Hello everyone, today in this video we'll be discussing the fourth module of operating system. This is a very short module which will be covering about the memory management techniques, and if you like this video, hit the like button and don't forget to subscribe to my channel. So before moving on, we need to understand what is virtual memory. See, we all know that there is memory inside the CPU and the secondary storage wherein we can store the data. So suppose that the memory is from 0 to 100, okay, and the process requires some memory and data, okay. So suppose that the process P1 required this much memory and it was given to that, okay. So this is still left here, and the second process P2 came and it took this much memory and this is left here, and P3 took this much memory and this is left here. And when P4 came, what happened is this much memory is there, it went on to take this one, because this one is a little bit only left here, this also is little bit left, and this is also little only left. So it can't take up the individual spaces here, it has to take this one, contiguous memory location. So it will waste a lot of memory, because if we combine all of these, it's sufficient for P4, but still it will take this one. So this is the wastage of memory. To avoid this, what we can do is we can use the concept of virtual memory. In virtual memory, what happens, the virtual memory manager will tell to the processor that if you want this much space, yes, take it, you will have this much space. So process P4 will think that it has got memory from 0 to 10, okay, it is a contiguous memory location. But actually what happens is, inside this, the this whole memory which is given to um, this memory which is given by the manager is actually the combination of these three. So the address of this and this and this will be stored inside this, okay, and that will be actually divided here, 0 to 2, 2 to 8. So these three parts are nothing but the combination of this, but to the processor it looks like it's a continuous memory location. And whenever a process requires this memory, it will see the address here. This is known as logical address, okay, the virtual address which is given to P4, okay, and the actual address is this one. So the conversion happens in the lookup table. This is known as lookup table, okay. So in this, if you want to know the memory location of 0 to 2 which is given to the process, 0 to 2 will be looked up here. What is the location of the first block here? That will be translated and that will be pointed to here. So nothing happens actually in virtual memory. Also it's the same memory, but just the way to show to the processor that the memory you can use here, that will be deferred, okay. So this is known as virtual memory. The next one is demand paging. Demand paging means the pages. Pages is nothing but the blocks of the memory, as I showed before. The blocks of the memory, right? These are nothing but the pages, okay. So pages are fetched from the memory only when it is required, okay. So that's known as demand paging. This is a 6-step process. In the first one, the processor will ask for the required page. At that time, the page will be checked if it's there in the cache or not. If it's not there, it will request to the operating system to fetch the page from the main memory. It will be sent to the free frame. Free frame is nothing but it will have the fetched memory locations in this area, okay. And after that, this will be sent to the memory location, and that will be sent to the processor, okay. So in this way, the pages are fetched only when it is required. This will save a lot of CPU cycles, okay. The next topic is copy on write. Copy on write means if you want to make any changes, see, there are two processes which are sharing this memory location. So if the process P1 wants to make any change to this, then P2 P2 will also see the change here. So P2 doesn't want the change here. So what is the solution for that? For that, P1 can make a copy here and make the changes here, okay. So the original one will be preserved for P2. So this is known as copy on write. The next one is page replacement. See, as I told you about frames, frames means that's an area where you can store the pages fetched from the memory, okay. So page replacement means once the frame is full, we have to replace the existing frames, one of the frames, to allocate the space for the new page. So the way in which we choose which one should be replaced, that's known as page replacement algorithm. This is the RAM which we have been given with, and we have 3 frames empty, okay. So we have 3 frames here and 20 page requests. So these are the page requests which we have to fill here, okay. And the result is in 15 page faults. So after filling all of this, we'll get 15 page faults, okay. So what does page fault mean? That will be looking here, okay. So to start this, firstly, it's a FIFO page replacement. So the first three will be writing here as it is because it's not present. Whenever the page which we are requesting is not present, we'll mark a star here, okay. So since 7 was not present, I wrote 7 here and marked a star here. Okay, and then 0. First page is already filled with 7. Second, I'll write here 0. Whenever I write a new page, I'll write here as star. Then 1. Again, I'll write a star here. Then 2. See here, first in, first out. That means 2 should be replaced with 7, 0, or 1. Okay, so which one I will choose? First in, first out. First in was 7. So I'll replace 7 with 2 and I'll write 0 1. Since I replaced, I should make a star here. Then 0. 0 is already present. I need not do anything. I'll mark here as H. Okay. So when I don't do anything, I'll mark here as H. Okay. Then 3. I have to replace 3 from either of these. Okay. So which one I'll replace? The first one which was in. That is 1. That is 0. See here, 0 came here first. So we'll replace 0 with 3. Then I'll mark a star here. Then 0. I have to replace 2, 3, and 1. Which was the first which came in? It was 1, right? 1 was from the 1 was for the longest time in this RAM. So I'll be replacing this. I'll be replacing 1 with 0, and I'll mark a star here. Then 4. 2, 3, or 0. Which one came the first? See here, 2 came from here, 3 came from here, 0 came now. So 2 was the first. So I'll replace 2 with 4. 4 3 0. I'll mark a star here. See, in the similar way, I'll fill out the rest of the things also. After filling these values, I'll count how many hits I have. 1 2 3 4 5. Okay, so I'll write here page hit is equal to 5, and the remaining one are the faults, which are 20 minus 5, and it is 15. So I've got page hit and page fault, and now we have to find out the hit ratio and fault ratio. Now, what is the formula for hit ratio? Total number of hits divided by the total number of requests. Okay, so it is 5 by 20, and the fault ratio is the total number of faults by the total number, which is 15 by 20. Okay, so this is the hit ratio and the fault ratio for FIFO algorithm. There is a small theoretical topic which is Bilady's anomaly. It's very important topic. It says that for some page replacement algorithms, the page fault rate may increase as the number of allocated frames increases. Means, see here, the allocated frames are this one. Okay, if I increase these frames, there will be more chance that the all the things will come in the same place. But according to this anomaly, for some algorithms, when we increase the number of allocated frames, the page fault also increases. That's the anomaly noted in the FIFO algorithm. Okay, so to overcome this, we'll be using optimal page replacement algorithm. Let's see how to do that. See here, what does optimal page replacement algorithm say? In this, we'll be knowing in advance what is the string which we are being given with. Okay, so if the user enters these values, so the computer system will know what are these values, whole values. Okay, so the whole list will be in front of the computer system. In the previous one, it was in real time. Means the computer system doesn't know which request will be made. Okay, but here we already have the data. Okay, so now let's start the optimal page replacement algorithm. In this, we'll do the same thing. First 7, then 70, then 701. Okay. Now we'll be checking for 2. Which among 70 and 1 will be used at last? See here, 7 is repeating at the last. 0 is repeating here. 1 is repeating here. So 7 is repeating at last here, right? So we can replace 7. 201. Then 0. 0 we already have, so it's a hit. And 3, you have to replace from 201 with 3. So among 201, which is repeating at last? 0 is here, 2 is here, 1 is here. So 1 is repeating at last, so I can replace 1 here. So I'll be writing 203. And 0, 0 is here, so I'll be writing 203. It's a hit. And 4, see, 2 is repeating here, 3 is repeating here, 0 is repeating here. 0 is repeating at last, so I can replace 0 with 4. I filled the remaining values. Now I'll be noting down the page hits and page faults. How many hits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and page faults are 9. So the hit ratio and the fault ratio will be 11 by 20 and 9 by 20. Okay. This is the third one. This is LRU page replacement, which means least recently used. So we'll be doing the same thing here. 7, 70, 701. Now for inserting 2, what I have to do, I have to see which one was least used, means which was least recently used. One was used here, and 0 and 7. So 7 was least recently used, so I'll replace 7 with 2. I'll write here 201. Okay, and 0 is here, so it is a hit. And 3 among 201, which was least recently used, it is 1, so I'll replace 1 with 3. 0 is here. 4 among 203, which was least recently used, um, 2 is used here, 0 is here, 3 is here. So among these three, 2 is least recently used, so I'll replace 2. After filling the table, you have to calculate the number of page hits and number of page faults. The fourth one is LRU approximation page replacement. In this, 8 bits are used, which show if the page was recently used or not. So 8 times. See, suppose that the processor checks for each second that the page, how many pages are being used, and it updates this value. So in 8 seconds, previous 8 seconds, if a page was not used, it will all be 0. If it was used in some seconds, like 2, 4, and 5 seconds, it will be made as 1. By using this information, we can decide which page to replace and which page not to replace. Okay. The fifth one is counting based page replacement. That means in the previous like 1 minute, how many times the pages were referenced, means how many times it was used. So that will also be written here. That count will be separately stored. So by using that count of page references made, the decision will be taken which page to replace. In page buffering algorithm, a free frame list should always be maintained. So suppose that the frame is of 10. Okay, 10 frames are free, but at least two should be free. Even if 8 is filled, 2 should be free. And in case 8 are filled and again we want another frame, at that time we have to free one page. At that time, what we will do, the page which we want to free, that will be noted down here, and that will be sent to the RAM, and RAM will send the page to the main memory. So the page which is being to be replaced, that will be stored in the memory, and in that place where it is now empty, the page which we stored here, that place is empty now. In that place, the new page will be stored. Okay, so that's known as page buffering algorithm. Allocation of frames means we have a set of frames here, and there are two processes which are differing in the size. One is 10 KB and another one is 127 KB, and we have 62 frames free here. So at that time, how many frames will be given to this and how many frames will be given to this? There are two ways. First one is 62 into 10 by 137. The formula is this size divided by the total size, means 10 by 137 into how many frames are there. That will give us approximately 4 frames, which will be given to process 1. And for the second one, 62 into the total number of frames into 127 by 137. 127 is the process size divided by the total size. That will get as 57, and 57 frames will be allocated to process P2. So the bigger the process is, the more number of frames will be given. Okay, this is known as proportional allocation. The second one is equal allocation, means it will be m by n. M means the total number of frames which are there, like in previous case 62, and n is the total number of process, which is in the previous case 2. So 62 by 2 is 31. So each of the process will get 31. Okay, 31 frames. To understand thrashing, you need to understand what is multiprocessing. See, this is the RAM here, and there are multiple processes here. So to allocate this whole process in the same RAM, it's not possible because process is very large, and all the process can't be allocated in the same RAM. So what we will do is we will take one part of the process which is currently executing, that will be storing here, and the next one here, and the next one here. So in this way, all the process can be executed simultaneously, because at the same time we need not require all the part of the process, right? So the only required part will be stored in the RAM, and that will be executed. Now the problem comes when the page 2 will be needed. See, all process page 1 is being stored in the RAM. When this is over, we need the page 2. So page 2 should be replaced here, then page 3. So when it happens at a large scale, um, I mean, when multiple processes are there, like 100 or 200 process, at that time, it will take a lot of time to fetch the page from the process and store in the RAM. So in that way, what happens is the efficiency of the computer will become low, because it will take a lot of time to fetch from the memory and store in the RAM. So in that only, most of the resources are utilized, and we can't perform the program efficiently. So to avoid this, what we can do is, we can keep a count of the least used and most reference frames and page faults using the working set model. So if you have the information about which process is least used and which is most used and which is more important according to different priorities, so in that way we can set a upper bound and the lower bound of the limits for each process. Okay, so by using that, we can make the working of the RAM more efficient. Is about file system, and it's more easier than the previous one. In this, we just need to know a few concepts regarding the file managing systems. Okay, so basically we need to know what is directory and collection of related files. Directory means all the files which are stored inside the memory. Okay, and each file will have a set of related files. That's known as collection of related files. Okay, and for each file there will be file attributes like name, identifier, type, size, location and all. And file operation means you can create a file, write on it, read, reposition, delete, and there are file types like exe, txt, .c, or a image or a movie. Okay, so those are the file types, and the file structure is of two types. The first one is the raw data structure. That means inside the memory the files will be allocated different sizes for the different types of files. Okay, and internal file structure means in each file, see, this part is expanded here, and in each file you'll have two parts. First one is for the design part and the visual part, and the second is the coding part. So this gives the design of the file, and this gives the logic of the file. Okay, and there are three methods to access the files. First one is sequential, if the files are arranged in the form of an array. And the second is direct access, means if we know the address, we will go to that address and fetch that file. And the third one is indexed method. Indexed method means there will be a table where we will have all the locations for the files present inside the memory location. So if you know the index number, we can fetch the particular file. Let's discuss some points about the directory structure. See, when you open your computer, at that time, if you open my files, at that time you will have many folders in this part, right? That all are directories. Okay, and if you open one particular file, you will have many files here. Those are known as files which are the user files, and these are the computer directories. Okay, there are many types of directories. First one is single level, means the directories will be stored at one part, and the files will be which are associated with the directory will be stored in the under each directory. Okay, the second is the two level, means if someone wants their own directory, at that time we can use the master directory, where it will have all the user directories stored, and for each user directory there will be the files which are related to the particular user. Okay, so that's known as two level directory. In tree structure directory, there will be no two levels, like there can be more than two levels, and for each level there will be one particular, like user directory, or the files will be related, or in the, like for the first one it is root, the second it is users, or the third one can be ended with the files, or if it's more expanding, the third level can also have the other user directories, and at the last level all should be files. Okay, acyclic graph directories are used when two or more files or directories need to share the same file. Okay, so in that time acyclic graph directories can be used. And the second point is, only from top to bottom it can point. Okay, unlike the general graph directory, where you can have the points from the directory to the upper directories also. Okay, in the previous one, acyclic means there should be no cycle, only from parent to child. And in general graph directory you can have cycle also, means to the upward also. Okay, and file system mounting means the the files stored in the form of a tree structure, means the related files will be stored here, which are the most priority will be stored up, and the least priority will be stored down, and the whole group will be stored as a part of this tree. Okay, like that many parts will be made. It will be more useful and efficient for searching any element among these nodes. Okay, file sharing means the same document being accessed by multiple users around the world. Okay, so it's very important that the data which is being accessed by everyone should be authorized to access. Okay, for that we can set the access specifiers, like for remote access, client server model is used. Client server model is, if you have a device here and you need to access something from the server, you need to have the login ID for the private data. Or if it is a website and it is made public, you'll have three options: either you can modify it in the public, or you can modify your private data, or you just have the access to read the data, you can't make any changes. Okay, so for all of that, the login is required, and since it's a website, everyone has access to it. It's known as distributed information system. And to keep the data safe from the unauthorized users, there will be many access methods. Like what are the possible file operations: read a file, write a file, delete, append, list, and execute. Okay, so it depends on what all access will be given to the users. So there are three types. First one is owner. Only owner can access these files. Or users means which users are authorized to access. Or universal, which means anyone can access. Okay, and the next option is the setting of passwords, which means who has the password, those people only can access the data. Okay, let's talk about the file system structure. The file system structure has two main parts. First one is the user's view, means how the user views the data in his system. Means if he clicks one button here like files, all the directories will be opened, and then the inner levels of the files will be opened, and then the documents will be viewed. Okay, so this is the user's view. And second one is storage, how these things are stored inside the memory. So those methods of storing the files are discussed under the topic file system structure. So basically, it's a five-step process. At the most lower level, the magnetic disk stores the data, and by using the device drivers, we can translate this data into a raw data, which will be stored by the basic file system. It will not be organized. Okay, and to organize the data, organization module will be used, and then finally the apps which use the data will be able to process the data and show to the user in the screen. Okay, by running and executing the code and the program. Okay, the next one is file system implementation. To implement any file, you need to run the computer system. For that, a boot control block is used. It has the information needed by the system to boot an operating system. After that is done, you need to have the information regarding the files being present inside the memory locations. Okay, so it contains details such as the number of blocks, partition size, pre blocks, and all. By using this data, we can process the data. Means if you have to read some data, what we can do is we can send the function to read, and at that time memory will make a copy of the original data. It will not give the original data, it will make a copy of it, and that will be sent to the memory, and the changes and the reading will be made here. Okay, so the original data will be safe here. And for this also many levels are used. First one is master level, which will have the information regarding the user directories, and the user directories will have either the sub user directories or the main files only. Okay, so this is the hierarchy maintained for the file system implementation. So this is the hierarchy which I was talking about. First one is mounting. Okay, if you organize this data, it will be in this form. Okay, this is the raw data, means all everything is mixed here, it's not prioritized or organized, and by using this we can form the table here. In this, the main root will be here, the root data, and then the basic files, then the user directories, then the user files, and then the main application. Okay, so the complexity is being reduced here, and what we access is only this part. This all is inside the main memory. Okay, we can't access this one. Okay, till now what I discussed was about the physical memory, means the main secondary storage. Now let's discuss about the virtual file system. Means as I told you before, the process requires the main storage here, so in between that there will be virtual memory. And to manage this virtual memory also, the same things what all I discussed before, that will be applied by this also. That's known as virtual file system. Okay, so it has four things: in node, file, and superblock and dentry. In node represents an individual file, and file represents how many open files are there, and superblock represents the whole file system, and dentry represents the directory. Okay, and the operations include open, write, read, mmap, and close, and there are many other operations also. The same things which are discussed in the physical memory will be applied in the virtual memory also. Okay, now, just as how we discussed about the file system management, we have directory implementation also. There are two ways to allocate and manage directories. First one is linear list, means all the directories are stored in the form of an array in the contiguous memory location. Or the second one is hash table. Hash table means it's just like an index. We'll have the number here where the actual directory is stored, and by using a hash function, we can know what the number is. Okay. So all the files are present inside the memory. Now we'll be discussing how to allocate those files in the memory space. Okay, these are unorganized. How to organize those, that we'll be discussing. The first method is contiguous allocation. That means inside the memory, these are the numbers 1, 2, 3, 4, 5, 6, like that. We will be storing the files in the order. Okay, that's contiguous memory allocation. Second is linked list, which means this memory will have the address of this one, and this will have the address of this one, and along with the address, the data will also be stored inside this. Okay, that's known as linked allocation. The third one is indexed allocation. There are two types. First one is single level. That means the only this part will be there. For now, consider this part only. In this, what is the address of this? It will be stored in this table. Address of this, it will be stored in this table. So if there are multiple like these tables, it will be very hard to manage these. So for each of these table also, one main table will be there. So if we are considering only this much, it is single level for small systems. Okay, and for larger systems, it will be usually multi-level. Okay. Lastly, let's discuss about the free space management. In the free space management, how much free space is left, that is to be managed, and it's very important to maximize the efficiency. The first method is bit vector. In bit vector, we'll have two parts. First one is 1 or 0. 1 means a free bit, or 0 means an occupied bit. Okay, so this bit vector here. So where all 1 you can see at those memory locations, it's empty, and you can allocate the resources. Okay, so that's about the bit vector. And second one is linked list. It's the same as the previous one, but in this case it keeps a list of all free blocks. Lastly, in the previous case, it was how many blocks are allocated, those memory address will be pointed out by the linked list. Okay, means how many data will be there in which parts, those will be connected. In this, the connections will be between the list of all free blocks. Okay, so this is the second one. And the third one is grouping. Means, see, if there are 10 nodes, okay, 10 nodes free, so the first one will be storing the address of the next 9 nodes. Okay, so that's known as grouping. And the fourth one is counting. Counting means if there are many arrays, means contiguous memory locations stored here, like an array from 0 to 10, and second array 200 to 300. So if there are many arrays like that, what we can do is we can allocate a part of the memory to store the address, starting address of each of the array. Okay, so 0 will be stored here, 200 will be stored here, and the remaining how many address are there, that will be stored here. Only the starting address need to be stored because it's contiguous memory location, it's continuous, so we need not store the memory location of all of these. Okay, only starting address will be sufficient. That's known as counting. And the last one is space maps. It's a new concept introduced, and in this, what we'll be doing is we'll be storing the free blocks in the form of a tree structure. Okay, to know which all which all nodes are free and which all nodes are occupied. Okay,